reflection of light. Without light, we would not be able to see anything. And all objects are visible because they reflect light. So if you're able to see this table, it is reflecting light. Light has many properties. Reflection and refraction are two of those that we'll look at today. But there is interference, polarization, diffraction, scattering, photoelectric effect, and so on and so forth. We'll be looking at some of the other properties in the other chapters. Every chapter in physics depends on laws, right? There are two laws of reflection, two very important laws of reflection. This is what you see there in the diagram is the first law and the second law, actually. You see the incident ray, it is the ray that falls on the surface, that's the surface that reflects light. This is, as you can see, a perpendicular drawn to the surface. The angle between the incident ray and that line, the perpendicular, is theta I. It's called the angle of incidence. Now, the reflected ray goes in such a way that the angle of reflection is always equal to the angle of incidence. Always. So that's the first law of reflection. Theta I is equal to theta R. All the time. Doesn't matter whether the surface is plane or whether it's curved, or whatever it is, if light is reflected, that law is always followed. And the second law, which you may not realize, but which makes it very convenient for us geometrically, is that all three, the incident ray, the normal, and the reflected ray, all lie in the same plane. As you can see, it's all in the same plane, plane of the board, plane of the screen right now, isn't it? Because if only the first law was to be satisfied, then the reflected ray could have gone in any plane. If it is just the angle to be equal. But now it has both got to be satisfied. Those are the two laws of reflection. The angle of incidence is equal to the angle of reflection. The incident ray, the reflected ray, and the perpendicular lie in the same plane. Yeah, I've just written law of reflection there, or it could be laws of reflection. We'll also look at reflection from smooth and rough surfaces. That is what you see now. That's called irregular reflection. Is the surface of the table smooth or rough? It appears smooth, but if you look at it through a microscope, it's going to be really rough. That's why you cannot see your face in the table like you do in a plain mirror. Can you see your face here? Comb your hair using the table? That shows that it's rough. You understand that? If it's smooth enough, then all the rays will be reflected in one direction. As you can see here, they're not reflected in one direction. That's why you can't get an image, but you can see the object. So that's the difference between irregular reflection and regular reflection. Oh, that's reflection in a plane mirror. The thing that we use almost every day, spend hours without knowing what it is. Let me tell you that as people think and as they try to cheat as always, to get your full image, you do not need a mirror that is as big as you. That's what they try to sell us in stores. But as you look at this diagram, you see that that mirror has a particular length, as you can see, right? That's all that is required to get the full image. But it has to be at a certain height from the ground. So you got to do this and send it to me for extra credit. Find out the minimum length of the mirror and how high it should be off the ground to get a full-size image of a person. And let me also tell you, it doesn't matter how far away you stand or how close you get. Because most of you may be thinking, well, it depends on how far away you are. No, it does not. It does not. So that's interesting, but I'll give you a clue and watch carefully. The incident ray that starts from the top of the head falls there and is reflected in such a way that the angle of incidence is equal to the angle of reflection, isn't it? So if that ray gets into her eye, surely she can see the top of her head. Do you agree? Similarly, if the ray that starts from the toes or from the bottommost part of the leg, the feet, if that ray gets into her eye, then definitely she can also see that point. You understand this geometrically? So, and you know that these two angles are equal. And again, if I had drawn a perpendicular there, the angles would have been equal. So with that geometry, you can easily calculate the length of the mirror. But when you send the extra credit, you'll have to send me your height. And you'll have to measure the depth of your eyes, the distance of your eyes from the top of your head. Ask somebody to help you do that. Don't you think that it matters? Okay, so it should be tailored to your height and your features. And then you have to get the minimum length of the mirror and how high it is from the ground. Whenever you look at an image, there are four properties. Four properties of an image. Is that the next screen? Let's see. Yes. Then we'll go back to the previous one. The first property is called a nature. The nature of the image. The nature of the image could either be real or it could be virtual. Either real or virtual. Okay, let me tell you the difference between these two. When you look into the plane mirror, the image that you see there, can you touch it? Can you project it on a screen? Come on. Can you project that image that you see in the plane mirror on a screen? Just like the image that you see on a television is of course projected on a screen. Now I'm asking you, can you do that with the image that you see in the plane mirror? You can't, which means it's a virtual image. The image formed by a plane mirror is a virtual image because it cannot be produced on a screen. So this is the basic difference. If you can project an image on a screen, it's a real image. If you think there is an image, but you cannot project it, then it's a virtual image. We'll get to that. Second thing is the type of image. Some images are upright, the others are inverted. If you're trying to shave your face, of course, an inverted image is of no use. You'll cut off your nose or something. So it depends on what you're using it for. Or like if you use a mirror that produces an inverted image as a rear view mirror in your automobile. If it's an inverted image, is that useful? Inverted image? I saw somebody shake their heads.
Not very.
Because if you see the inverted image of a huge truck behind you, you're going to be scared to death. Okay, so type of image could be upright or inverted. Size of the image, there are three possibilities. What are the three possibilities?
Smaller.
Magnified, which means bigger, smaller, or same size. Bigger, smaller, or same size. And the position of the image can be at different points. We'll look at that. So basically, when you look at any image, there are four properties you should think about. The nature, the type, the size, and the position. Let's go back to this image and look at all those. Okay, first of all, is this real or virtual? I heard both. It's a virtual image. The second reason why it's a virtual image is because you see the reflected rays. Take a look again. One reflected ray is this one, isn't it? Coming into your eyes. If it had kept on going, it would have gone that way. Which is the second one? This way, isn't it? Do the two reflected rays actually intersect? Do the two reflected rays actually intersect? Look at the dotted lines, please. This reflected ray is going that way, isn't it? Will it actually intersect, the two reflected rays? Or do they appear to intersect? It's appearance. They appear to intersect, so that is why it is a virtual image. More on that as we go. Now, what about the size? Same size. Is it upright or inverted? Upright. And what about the position? What is it? Look at the position. Same distance behind as the object is in front. Now, DO is called the object distance. It's going to be measured from the reflecting surface. So that's DO. This is DI. What's the relation between DO and DI? Give me the mathematical statement. DO is equal to what? Wrong. Somebody said it? Thank you. DO is equal to negative DI. That is called the law of distances for a plane mirror. DO is equal to negative DI. Okay, it's not less important because it's simple, okay? That's how some people take it. Oh, it's a simple formula, it's less important. No. DO is equal to negative DI. What does the negative show? It is formed as much behind as the object is in front. Okay. Spherical mirrors. Man always has an idea. When they made a plane mirror, they said, why can't we make a spherical one? And first of all, you have to understand what a spherical mirror is. See what I did. Those who are watching saw what happened. Did you? I drew a sphere and then erased that part to show you that a spherical mirror is a part of a sphere. Therefore, wouldn't it have a center? The center of the sphere. That is what I have marked there. So that's a center. It is called the center of curvature. That is the center of the curve. All right. And if you take the geometrical center of this mirror, geometrical center, measure the length and take the center, wouldn't you get it somewhere here? That's called the pole. So now you have two centers. One is the center of the sphere, the other is the center, geometrical center of the mirror. The line joining them is called the principal axis. The principal axis. Okay. Line joining the pole and the center. Now, if you have parallel rays fall on, oh, what is that? That is showing the non-reflecting surface, the shading. So which surface is reflecting? Like the palm of my hand now. The inside of the sphere is reflecting. Okay. If you have a parallel ray fall on a concave mirror, it will always pass through a particular point exactly between P and C. That's called the focus. That is called the focus. So what do you mean by the focal point or the focus? Parallel rays. Where do parallel rays come from? From infinity. So if you turn the concave mirror towards the sun is at a great distance away from us, isn't it? So it's almost at infinity. Where would you get the image of the sun? At the focal point. How big would it be? You know how big the sun is, but the image would be a point. So it's extremely diminished, right? The image is extremely diminished. Now, because it's a point, we can't say whether it's upright or inverted because it's a point. But we'll soon see. So remember this. When an object is at infinity, where is the image? At the focal point. Is this a real focus or a virtual focus? Are the rays actually intersecting? Yes, it's a real focus. Real focus is taken as positive. All real distances are taken as positive in calculations. I told you. So a concave mirror has a positive focal length. So in a problem when you read it's a concave mirror, 15 centimeters, you're going to say F is plus 15 because it's real. Okay. That is what I'm trying to write now because it's very important. PF is the focal length. All distances are measured from the pole. So PF is the focal length. It is real for a concave mirror. Now, let's take a look at a convex mirror and see how it is different from this. All right, again you see what I do. Okay, that's a part of light. So let's go into refraction of light. Refraction of light is the bending of light when it passes from one material into another. That's it. But why should light bend when it goes from one material into another? Because of the change in speed of light. For example, well, we all know that the speed of light in air is 3 times 10 to the 8 meter per second. I think I picked the example of glass. In glass, the speed is 2 times 10 to the 8. Would you say that that's just a little bit smaller, or is it drastically reduced? Drastically reduced. Now, if you take the ratio of the speeds, you would get 3 by 2, because the 10 to the power 8 will cancel out and you get 1.5. That is called the refractive index of glass with respect to air. So I've already given you the definition for refractive index now. Did you get it? What is the There are 4 definitions for refractive index, but this is the best one. Refractive index is the ratio of speed in a material, speed in air divided by the speed in the material. Refractive index is the ratio of speed in air divided by the speed in the material. Okay.
So it will always be greater than 1.
What you see coming up on the screen is actually an incident ray. Clearly understood, that's the incident ray. That is the normal or the perpendicular drawn, right? And that is the surface separating the two materials. So you have air and you have glass, and the light ray was supposed to go straight like that. Is that clear enough? But do you see how it bends? It bends towards the normal. Didn't it go towards the normal? Because it's going from a less dense medium to a more dense medium. But what if it was going the other way? It would bend away from the normal. So that's another point to be noticed. If it goes from less dense to more dense, goes towards. If it goes from more dense to less dense, away. Didn't I say that everything in light is reversible? So if the light ray had been going into glass, from glass into air, you can easily understand it would go away. All right. Okay, let me build it up on what I did. That is theta I, the angle of incidence, that is theta R. And when you write it like this is how you read it. Refractive index of glass with respect to air. Refractive index of glass with respect to means compared to air. And didn't I tell you that it's defined as the speed of light in air divided by the speed in glass? I gave you the numbers too. 3 times 10 to the 8 meter per second divided by 2 times 10 to the 8 meter per second. So you get 1.5. Refractive index does not have any unit because it's just a ratio. So when we continue into refraction, this time it's going from air into glass. Isn't that what I did before? It's the same thing. But I want to teach you the law. It's called the Snell's law. Not the Snail's law, but Snell's law. That's the name of a scientist. A simple law. Where I'm going to label this as N1 and this as N2. I hope that doesn't matter. Because it could have been NA. You know, what's N1 in this picture? What's N1? Give me the number. What's the refractive index of air with respect to air? 1. Okay. So, according to Snell's law, N1 sine theta I is equal to N2 sine theta R. Finished. But you got to be very careful. N1 sine theta I. You multiply the refractive index with the sine of the angle in that material. You understand? Don't cram that formula. Take it that way. Multiply the refractive index with the sine of the angle in that material. Let's do a problem. If theta I is 50 degrees, let's find theta R. Go ahead. Theta I is 50 degrees. So what happens? N1 is 1. Sine 50 is 1.5 sine theta R, because that's glass. You get sine theta R is sine 50 by 1.5. 0.51. Take the sine inverse of that. You get 30.71 degrees. Proving that theta R is less than theta I. Proving that it's bending towards the normal. Is this all clear? That's Snell's law. Internal reflection. the show. Anyway, let's see. Take a look at this. The first one. It's going from water into air, isn't it? Okay. Does it bend away? Yes. If you keep on increasing the angle of incidence, isn't this having a bigger angle? It keeps bending further away. And for a particular angle of incidence, what is the angle of refraction here? 90 degrees, for those who are paying attention. That angle of incidence is called the critical angle. So what is the critical angle? It is the angle of incidence for which the angle of refraction becomes 90 degrees. What's the meaning of the word critical? Means boundary. When you say somebody is critically sick or ill, you're saying he has a chance of passing from life into death. Boundary condition. That's the meaning of the word critical. Okay. So why is it the boundary condition? Look at that again. If you further increase the angle of incidence, like in this one, the ray, instead of passing out into air, returns into the medium. But that's not refraction. Isn't that reflection? But remember, that is reflection due to refraction. It's called total internal reflection. Why is it called total? Because, look, if we are very sensitive and clear, you'll understand this. At this point, anybody agrees that a part of the ray would be also reflected? A small part? I'm saying if you're underwater and look at yourself, you can see a slight image of yourself. Can't you? Yes, that's because a part of it is reflected. And the major part is refracted. Same thing happens here. Correct? Same thing happens here. But here, there is no part that goes out. It is totally reflected. That make more sense? So which would give us the sharpest images? Definitely total internal reflection, isn't it? And so that is why it is called total internal reflection. There are two conditions for total internal reflection. What are they? Number one, the ray must be passing from a more denser to a less denser. Right? Number two, the angle of incidence must be greater than the critical angle. Must be greater than the critical angle. Theta C is called the critical angle. We know that. Conditions, I gave you the two conditions. What are the two conditions? Light should pass from, now I have to say, a more optically denser to a less denser medium. Okay? Number two, the angle of incidence must be greater than the critical angle. This is what makes diamonds so precious. You know that diamonds are forever. Okay? It makes it so precious because of total internal reflection. What? Refraction through a prism. Yes. Stop. That's the prism. Outline of the prism. Incident ray. Slow down. Isn't it moving from air into glass? Let's assume that it's made of glass. Okay? That's a part of a sphere, again. Oh no, I'm trying to draw the image of a concave mirror first. When the object was at infinity, where was the image? At the focal point. Now I have brought the object closer, as you can see. Isn't the object closer? You need two rays to find the image. Two rays at least. A parallel ray always goes through. A parallel ray, after reflection, always passes through the focal point. And didn't I say everything is reversible? So if I draw the second ray already passing through the focal point, after reflection it should become parallel. Is that easy? Did you get that point? So you see the first ray is parallel to that, goes through the focal point. The second ray already passes through the focal point, so it has to go parallel to the principal axis. Do they actually intersect? Yes. So shouldn't that be the head of the image? Because those two rays started from the head of the object, correct? So that will be the head of the image. So we assume that all of the points will be straight below it or above it, and so you get the image. Give me the 4 properties of this image. Real or virtual? Real. Size. Smaller, inverted, and position between F and C. Isn't it between the focal length, the focal point and the center? Yes. Okay.
Wouldn't it only be inverted after the focal point?
So depending on the position of the object, the image is going to change. What are the properties of this image? We discussed that, right? All the 4 properties. Let's move on. The object is OA, the image is IB. It's real. That's too slow. Inverted, those are the properties. And on the exam, you will at least be asked to draw 2 figures. At least 2 figures. Between F and C. Okay. Now I want to show you how a virtual image is formed by a concave mirror. So, a concave mirror can produce both real and virtual. Okay. But note the position of the object now. Please, where is the object? Where is the object? It's very close. Between P and F, isn't it? Okay. A parallel ray, what happens to the parallel ray? Goes through after reflection, goes through the focus. And now I have to draw another ray in such a way that the angles are equal. That's falling at the pole, as you can see, and the angles are equal there. This is the angle of incidence. This is the angle of reflection. Will these two intersect on this side? No, they're going further away. They are diverging, isn't it? So now you have to imagine. And when I tried to imagine, I knew that it would go out of the screen, so I made a small adjustment. Please don't do that on the exam. Do you see the adjustment that I made? Right on top, I bend it a little bit. Do not. You have to extend it straight back, but if I did that, it would meet outside the screen. Is that clear enough? So, all right, what are the properties of this image? Virtual? Now you know why it's virtual, because the reflected rays don't actually intersect. They appear to be coming from some point. It's upright, it is magnified, and it's behind the mirror. So if you're using a concave mirror to shave your face, do you want the image to be upright or inverted? And do you notice that this is the only time when a concave mirror produces an upright image? That means you have to hold your face very close to the mirror, isn't it? Because your face has to be between P and F. So if you move it further away so that your face is beyond F, you're going to get an inverted image. At least that makes sense. Otherwise, the whole thing is wasted. So as you shift the concave mirror towards your face, you can actually see it. First, you will see inverted images getting bigger and bigger and bigger, then it vanishes, and then you see an upright image magnified. So you can use it as a makeup mirror, or to cover the holes on the face and make yourself beautiful until it rains. You can use this. What's the normal? Then again out. I'm drawing the 2 perpendiculars to the surfaces. Doesn't that appear to be at 90 degrees? To that one, and then another one at 90 degrees to this. This is the angle of incidence. I call it theta 1. That's theta 2, theta 3, and the outer angle is theta 4. Okay. So there are 4 angles involved. That is the angle of the prism. And this is the angle of deviation. Wait, what is that? What is angle of deviation? Let me ask you this. Did the 2 bendings take place in the same direction or opposite direction? In the actual sense of the word. It was supposed to go up, you can see. It first bent, look, it bent. And then again it bent. So wasn't it bending in the same direction both times?
Yeah.
And so the D that you see there is the total bending. Can't you see that I have extended the incident ray? Watch. Isn't that the way it was supposed to go? Isn't this how it's coming out? So isn't that the total bending? Hello? Yes. Therefore, wouldn't this, tell me what this angle is. What is this angle? Somebody. What is this angle? I'll show you again. This angle. You see what I'm pointing at? What is that angle? It is not theta 3. It is not theta 2. It is theta 1 minus theta 2 before you spin your stories. Because you see the total, look, this whole angle is theta 1 because they are opposite angles. You see that? And therefore, since this is theta 2, this is theta 1 minus theta 2. And so too, this one is, well, I'm going to call this theta 4. So this will be, come on, theta 4 minus theta 3. And if you add this angle with this angle, you must get D. Because D is the total bending, isn't it? Even otherwise, in a triangle, that is the exterior angle, should be equal to the sum of the opposite interior angles. I'm going to use that. So there is geometry there. So that's theta 4. Okay, even before that, I'm going to say theta 2 plus theta 3 is A. And somebody tell me why. Theta 2 plus theta 3 is A. I have to give you time. So. Here. Look at the figure that I'm showing you now. One side, 2, 3, 4. Isn't that a quadrilateral, four-sided diagram? And therefore, the total angle should be 360. But we already know that this is 90, and the other one is also 90, correct? Therefore, if you add this A and this angle, you must get 180. Right? Yes. And also we know in this small little triangle, if you add all the three angles, you should again get 180. So that means theta 2 plus theta 3 is A. Because didn't we just say that A plus that small angle down is 180? Didn't we say? A plus that angle is 180? Didn't we say that? And now we're saying theta 2 plus theta 3 plus this angle is 180. That means theta 2 plus theta 3 is A. Why is that equation important? Because A is a constant, but theta 2 and theta 3 are variable. Hey, tell me, if you change theta 1, would theta 2 and theta 3 change? Yes, but yet their sum must always be a constant. Because A is a constant. Because A depends on the geometry of the prism. That's why that's a very important equation. Did you get it? Okay, now I'm going to continue and get another equation. And let's see what we get. Didn't I already say that D is theta 1 minus theta 2 plus theta 4 minus theta 3. Did I say this? Did I? Come on. Did I say that? Yes, I did. The exterior angle is equal to the sum of the opposite interior angles. I already said that. Now let's rearrange that. We're almost done. And that's simple math, so you would know that that's correct. I hope everybody agrees that I can collect those minus theta 2 plus theta 3. Is that right? Is that right? Mathematically correct? But what is theta 2 plus theta 3? Okay, so I'm going to do that. So I can write theta 1 plus theta 4 minus A. And then bring the negative A to the other side. It would become A plus D is equal to theta 1 plus theta 2. Very important equation. I mean theta 1 plus theta 4 is A plus D. Underline both those equations. They are very important. You're going to be asked to solve problems. And finally, we're almost there. Can somebody apply Snell's law at that point? Can you apply Snell's law at this point? Oh, wait, I'm going to say that the refractive index of this material outside, what's the material outside? It could be water. Can't you put a prism in water? It could be anything. So just keep that in your mind. It's going to be N1 and the material of the prism is N2. Wait a minute. What's the material here? N1. Okay, N1. Not N3, okay? It's surrounded by material. Sometimes I've seen N1, N2, N3. Apply Snell's law here. what would you get? N1 sine theta 1 is equal to N2 sine theta 2, right? That's just like cramped. But the problem is, if you apply Snell's law here, can somebody try to say it? Because that's about the last thing we're doing today. Is equal to N1 sine theta 4. And if you say that, you got it. It's N2 sine theta 3 is equal to N1 sine theta 4. So whenever you apply Snell's law, no cramming will work. You have to think about what is the material, what is its refractive index, sine of the angle inside that. With these, we can do any problems to do with prisms. Okay.